Today I want to talk to you guys about pipelining, and hopefully by the end of today's lesson, you guys will be able to answer the following three questions. So we've already learned about a single cycle pipeline. We know it has a low CPI, in fact, an ideal CPI of 1, and it has a high clock period because we do so much in one cycle. We've learned about the multi-cycle architecture, which has a high CPI, but it has a low clock period. Now, the natural question to ask here is there an architecture that offers both the low CPI of a single cycle architecture and at the same time gives us the low clock period of a multi-cycle architecture? And to not to any surprise, there is an architecture and it's called the pipeline architecture. So let's see what that looks like and how it works. So we see similar hardware that we're used to with the other architectures, but we divide it into 5 different stages, namely the fetch, decode, execute, memory, and write back. What's also new here is you see these blue rectangles that divide each stage. These are flip-flops. They're basically the registers, and they store the work that was done in the previous stage to make it so it's readily available for when the instruction moves to the next stage in the next clock cycle. So say we have a computer program with many instructions. Let's call them instructions 1, 2, 3, and so on. So clock cycle 1, we fetch instruction 1. At the end of this clock cycle, it will write the relevant work that it accomplished into this register. And at the start of clock cycle 2, we will see instruction 1 has moved to the decode stage. And it'll successfully be able to decode because it has all the data that it needs latched into this register. Now, to really see the difference with a pipeline architecture, we have to take a step back and look at what happened in a multi-cycle architecture in the same instance. So here we have a multi-cycle architecture. So in the first cycle, we fetch instruction 1. It finishes fetching, and in the next cycle, it moves here. Now, the problem here is we've left all of this hardware, and this hardware is doing nothing. It is just sitting idle, not doing anything. What a pipelined architecture has to offer here, it says, well, why don't we give this fetch hardware some meaningful work to do that contributes directly to the completion of the program? So we say, well, let's just fetch instruction 2. And now instruction 2 is being fetched at the same time as instruction 1 is being decoded. Now, if we move forward a cycle, we'll see instruction 1 writes the relevant work it did into this register and moves into the execute stage. Instruction 2 writes its relevant work into this register and moves to the decode stage. And similarly, we fetch instruction 3. Also, the relevant work here, we will discuss in a later lesson what exactly that is. Now, this is the exact concept of pipelining. It allows the different stages of multiple instructions to overlap with one another. So while one instruction is being fetched, another one can be decoded, another one can be executed, another one can transact memory, and another one can complete. So if you go back to the questions that we started with, why was pipelining introduced? Well, it was introduced because we set out to find an architecture which offered a low CPI as well as a low clock period. So we can answer that question confidently. What is pipelining? Well, we saw that it's the sequential in-order execution of a computer program through this kind of a pipeline. And the key part there being is it allows the different stages of multiple instructions to overlap. So we can answer this confidently. Well, how does it improve performance? The most important thing to note here is, well, it allows us to utilize our hardware at all times. We never allow any hardware to sit idle if we don't have to. And to look at the clock period and the CPI specifically, let us move to a point in the execution where our pipeline is full. So we have instructions in every stage. Now, for a large enough program, this will frequently be the case. And if this is the case, then in any given clock cycle, we will have one instruction completing at any given time. And if we have one instruction completing in any given clock cycle, that gets us a CPI, an average CPI over a long time of 1, which is similar or actually equivalent to a single cycle architecture. For our clock period, it only needs to be as large as the longest delay of any of these 5 stages, which is similar to a multi-cycle architecture. So we can answer this question confidently. Now, of course, with all good, there is some bad to deal with. And here, the bad is there's additional complexities that we'll have to deal with and address when running a program successfully through this pipeline. And we'll discuss that in a later lesson. But to leave you with something to think about for now, think about what happens if you run a computer program through this pipeline, but it has instructions that are dependent on each other. And what I mean by dependent is they're dependent in terms of the registers that they use.